This chip can classify 2 billion images per second using light. The device, built by a team at the University of Pennsylvania, is more than 25 million times faster than modern electronic smart devices running image recognition AI models. This can be crucial for real-time image recognition applications such as those used in self-driving cars. At high speeds, correctly identifying a threat can prevent a disaster. But what makes the photonic neural network so interesting is not just its speed, but also its engineering. Unlike traditional neural networks which use electricity to perform calculations, this chip does arithmetic completely using light. Today, we are going to dive into how it works, what makes it so fast, and why photonic AI might be the future of image recognition. Welcome to Codeolences, my name is Jakub, and if you are interested in alternative, little-known computer technologies, you are in the right place. There are more videos like this coming your way, so make sure to subscribe to not miss them. Artificial neural networks are the foundation of every AI model, whether we are talking about LLMs such as ChatGPT, or apparently even AI-powered toothbrushes. Without going into too much technical detail, training and running a neural network involves performing a lot of matrix multiplication operations. It turns out that graphics cards are perfect for this task since they excel at parallel math. A central processing unit, CPU for short, might have a dozen cores, each capable of running one arithmetic operation at a time. GPUs, on the other hand, have thousands of cores, and that's why they became essential for deep learning. Image recognition in particular is one of the most computationally demanding tasks in modern AI. Every frame from a camera must be converted into numbers, fed through multiple convolution layers, multiplied by millions of parameters, and then classified. And often, all of this has to happen in real time. A self-driving car, for example, can't wait 50 milliseconds to decide whether the thing on the road is a pedestrian or a shadow. But here's the problem. Meeting those real-time requirements is often a balancing act between compute power and memory versus energy efficiency. Photonic neural networks, on the other hand, are artificial neural networks where computation happens using light, coming directly from the image. Instead of electronic transistors, they use on-chip optical components such as waveguides, couplers, and modulators, which, when set up properly, can perform the same mathematical operations just like a traditional electronic neural network. I'm going to explain all of this in a moment, but first, let's discuss what makes light such a special medium for transporting information. You see, light has several properties that make it uniquely suited for this task. Photons don't generate heat the way electrons do. They don't interact with each other, which means multiple signals can occupy the same space without interference. They can carry information across different wavelengths simultaneously, giving you information density that electronics simply can't match. Photons travel at the fastest speed allowed by the laws of physics. Using light for information exchange is not a new idea. In fact, the entire internet infrastructure already relies on it. I'm sure all of you heard about fiber optic cables that send data as pulses of laser light across thousands of kilometers with almost no loss, which is why global communication is as fast and reliable as it is today. What's interesting with this photonic chip is not the use of light itself, but the fact we are using it to compute. In the photonic neural network developed by engineers at UPenn, light enters the chip, propagates through optical neurons, and the pattern of interference, attenuation, and modulation creates the equivalent of weighted sums and activation functions. In other words, they physically perform neural network math in an analog way at the speed of light. This chip is the first fully integrated end-to-end photonic classifier able to recognize images directly as light and compute using optical propagation alone. According to the paper, the chip performs a full image classification in half a nanosecond, which is comparable to a single clock cycle on a modern electronic CPU. To understand how the chip achieves those speeds, we need to look at how it processes images at the hardware level. The image itself is formed optically on a 5x6 pixel array, which is further divided into 4 overlapping 3x4 pixel sub-images. This division into smaller patches is what we call a convolution, and even though it might seem counterintuitive at first, it is extremely useful. In traditional neural networks, convolution let the model build higher-level understanding of the data, while drastically reducing the number of parameters and improving efficiency. Instead of treating every pixel as an independent input, the network scans small, overlapping windows and applies a kernel, also known as a filter, to extract specific features, such as edges, for example. The same logic applies here. By splitting the optical image into overlapping subregions, the photonic chip is effectively performing a physical convolution. Using a waveguide, each 3x4 patch is routed into its own optical neuron, which analyzes that part of the image directly. There is no digital preprocessing. The hardware of the chip itself performs the convolution. In each neuron, the chip uses 500 micrometer long attenuators, which individually adjust the optical power of the input waveguide based on the learned weight, which was obtained in the network training process. To generate the output, a weighted sum of all neuron inputs is then passed through an optoelectric ring modulator that applies a nonlinear activation function. Specifically, the rectified linear unit, or ReLU. ReLU is one of the simplest yet most effective activation functions in modern neural networks. Mathematically, it outputs 0 for any negative value and leaves positive values unchanged. This may sound trivial, but it's actually very useful in practice. ReLU introduces nonlinearity, which is crucial for deep learning, and it also solves the problem of vanishing gradients. I won't go into too much detail on that here, as it's beyond the scope of this video. However, if you'd like me to make a video about the most common problems with creating AI models, let me know down in the comments below. Also, once you're down there, it will be the perfect time to subscribe, since 98% of people watching my videos are still not subscribed. Thank you. Now let's get back to talking about photonic neural networks. Instead of storing an image in memory, loading it, processing it, and passing it layer by layer, this chip lets light physically propagate through the network directly on chip at the speed of light. The final output layer consists of 2 output neurons, and therefore the classifier can be used for recognizing up to 4 different classes. The authors of the paper ran tests to measure the network's accuracy, meaning the percentage of properly classified images. The network was trained to recognize different handwritten letters, which is a common benchmark for computer vision implementations. The first test was based on 2-class dataset consisting of letters D and P. The second test had the chip distinguish between 4 classes, namely the letters P, D, A, and T. The photonic neural network achieved an accuracy of 93.8% on the first test and 89.3% on the second one. For comparison, the scientists also ran a simulation using a traditional neural network, which yielded a 96% accuracy on the 4-class test. As you can see, the traditional approach made less mistakes, but at the cost of greatly increasing complexity and speed. The simulated network used 190 neurons, while the photonic one has just 9 neurons, and it is literally a million times faster. The authors have compared their implementation to state-of-the-art computer vision devices, such as smart cameras implemented using Google's Edge tensor processing units. These devices can classify an image in just 15 milliseconds, which sounds good on paper, but not when you compare it to the speed of the photonic neural network, which needs just 570 picoseconds. This makes the photonic approach 26,300,000 times faster than the traditional electronic one. What I find especially incredible is that the authors believe they can make the chip even 5 to 6 times faster in the future by using better hardware. This would mean that it could be possible to classify an entire image in less than 100 picoseconds. But speed is only one of the benefits of photonic neural networks. Another notable thing about this chip is that it doesn't require memory, since all the calculations are happening by propagation on the hardware. This has both privacy and economic implications. Running a traditional image recognition model requires huge amounts of high-speed memory to store all the necessary information about the neural network. Currently, there is a global shortage of memory devices of all kinds, such as GDDR chips used in graphics cards, which, as we already discussed, are essential for training and running AI models. But as you probably expect, there are some drawbacks and limitations to the photonic neural networks. But before we get to that, I'd like to quickly tell you about FlexiSpot, the sponsor of today's video. FlexiSpot sent me their electrically adjustable heavy load E7 Pro desk, and I have to say, it's really good. I had a lot of problems with my previous desk. Whenever I moved or even typed on the keyboard, it would wobble a lot. My monitors and camera would shake constantly, which was honestly really annoying. The E7 Pro, on the other hand, is really stable, whether in standing mode or even during the height adjustment process. Speaking of which, I really like this electric height adjustment feature. With the E7 Pro, you get 25 to 50.6 inches height adjustment range. Working and studying long hours while sitting in front of the desk had me slowly turning into the Hunchback of Notre Dame, so E7's Pro feature to quickly turn into a standing desk is just awesome for me. The desktop itself is also really high quality. It's much thicker and sturdier than the one on my previous desk. Plus, cable management is just so much easier on the FlexiSpot desk since you get this magnetic cable cover and also a basket for your power adapter. If you'd like to upgrade your setup today, go to flexispot.com and explore the E7 Pro. FlexiSpot also offers massive sales right now, so don't miss out. You can also save an extra $30 on your E7 Pro standing desk by using my code Codeolences. Also, if you are on a limited budget, you might also want to check out the standard E7 desk. Click the link in the description to learn more. Thanks to FlexiSpot for sponsoring the video. Now let's talk about the limitations of photonic neural networks. The current chip operates on a very low resolution of just 5 by 6 pixels. This is definitely not enough to run the photonic network on a database such as ImageNet, which is typically used in computer vision research. Although the scientists have outlined a detailed plan on how to scale this technology to greater resolution, the current version is still more of a proof of concept, which still requires a lot of work and engineering to become useful in an industry sense. Furthermore, the training of the photonic neural network still happens electronically. The weights that are obtained from the electronic simulation are then applied to the optical attenuators that we already talked about. This enables the chip to achieve such impressive speeds and eliminates the need for memory. However, it also makes the chip less flexible, as any further fine-tuning requires work on the chip's hardware. Nonetheless, the researchers from the University of Pennsylvania believe that with faster photodetectors and improved fabrication methods, future versions could push classification times to even faster domains while operating on far richer datasets.